Tui, 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 tui a. Tui a I runga, tui a I raro. Tui a I roto, tui a I waho. Tui te here tangata tūturu whakamaua ki a tina, tina. Homi e, hui e, tai ki e. E tuaki nei o kei te mihi ki a koutou katoa ko I hui hui mai nei e tēnei ahi ahi. Kei te mihi, kei te mihi, kei te mihi. He mihi hoki mai I te mana whenua o tēnei takiwā nai tua herere. No mai haere mai ki tēnei rā, he rā whakahera mō tātou katoa. Ko te kaupapa o te rā, te hurihia, te ingoa hou o tēnei kura. He rā whakahera mō tātou. Ahakoa he mihi poto, he mihi aroha ki a koutou katoa, nō reira rauranga tērā mā, tēnā koutou, tēnā tātou katoa. So kia ora everybody, I stand here on behalf of the Office of Treaty Partnership at the University of Canterbury, but also acknowledge Nai Tua Hereri Mana Whenua for the university. And I invite and welcome you all to this very exciting occasion, the unveiling of the new name. And so this is a nice move for the Faculty of Engineering, and it also signals the journey that we are on as a university in regard to honouring our treaty partner, Nai Tua Hereri, as well. So just a short welcome to you all, but great to have you all here to participate in this auspicious occasion. Kia ora. And now I'll invite our tumu whakarai. Oh, sorry, I will invite whoever I'm meant to invite up to take over. Kia ora.
Thank you. Kia ora, everyone. Thank you, Liz. And those of you who don't know me, I'm Rajesh Takal, the head of Civil and Environmental Engineering Department from today, right, officially. And yeah, we would have a few welcome from our special guests who are attending our functions, special functions today. But I would like to just acknowledge the presence of our Vice Chancellor, Professor Cyril Delaray, and Executive Dean of Faculty of Engineering, Professor Saurabh Sinha, and our Assistant Deputy Vice Chancellor of Liz Brown, and Associate Deans, and special guests from industry, and our Engineering New Zealand Canterbury branch chair, Preetha McGibbon Robinson. So that, and Preetha is, because I want to give a little bit of introduction of her, because the next step involves her as well as with as our Vice Chancellor. So Preetha is one of our alumni. She completed Bachelor of Civil Engineering in 2011, if I'm not mistaken. And she currently works for Stantec as a principal civil engineer, and she leads the water team at Stantec. And she's also the chair of Engineering New Zealand Canterbury branch. And then we are also privileged to have her as our adjunct fellow in the department. So she has been really engaged with us in different ways. And she will be joining, of course, our Vice Chancellor, who doesn't need much introduction, so Professor Cyril Delaray, to unveil the new name of our department today. So may I invite Professor Ray and Preetha, please. Yeah. Thank you very much. Thanks a lot. Yeah. Next, I would like to invite Professor Saurabh Sinha, the Executive Dean of Faculty of Engineering, to welcome you all and to give us a little brief on actually how this move links with the faculty goal and strategy. Saurabh.
Tēnā koutou katoa. A mihi ana ki ngā mana whenua nā tuhururi ko sorab toku ingwa no Afrika ki ti tonga ahu, ko amamatua ahu ke ti kaupeka puhanga no reira, tēnā koutou, tēnā koutou, tēnā koutou katoa. Good afternoon, everyone. My name is Saurabh, as Rajesh has introduced, the Service Exec Dean. But I'm really here to welcome, but also thank the Civil and Environmental Engineering, the team led by Rajesh, but many have been involved, Sue, Rashmi, and quite a few within the department, as the strategic thinking is really something that has originated there in how we have arrived today. So maybe even before I say any more words, I think a round of applause is due to them on where we are. My plan is to say a couple of words about the context of the Faculty of Engineering strategy, talk a bit about the International Engineering Alliance, how the mapping thereof comes within a context of a strategic plan of an academic department. And thereafter, I'll have a short commercial break. And then I'll hand over to Rajesh. So that's the plan. And I know you have some things to look forward to. So firstly, when we were thinking about the strategy of the faculty, we embarked on a major consultation process, as is often the case. And we had the embrace of our stakeholders, internal and externally, with over 400 voices that came in touch with us in various ways and formats. But there was a strategic context, a framing question that we needed to put forward in such an exercise. And that strategic question has some leverage from a text on Soul of a University. But the strategic framing question was twofold. One was, what is it that we are good at? And that is a question you'd find quite resident in a university, as it is a question that frames our journey for excellence. And the second question was, what is it that we are good for? And that is a question that stitches purpose into our orientation. And you would appreciate that some of you who are in industry, you probably have had a similar framing question, and you would have also find that intertwine between purpose and profit, perhaps. So that was the framing question. And of course, when you then bring about the question of purpose, where does that lead to? What are the elements that would make us define in that direction? So one finds that there, we looked at multiple things. Sometimes when you look at strategy, it's like the various streams of a river that gives you that flow. In its persona, it can be quite beautiful, but if you're not careful, it can be a flood too. And it was in that persona that we found various aspects, such as the fourth industrial revolution, the fifth, the sustainable development goals was another. But the things like the sustainable development goals too have a timeline, such as 2030 in the case of the United Nations. So, but when you stand back and you look at the sustainable development goals, you would see things such as the planet, such as people, such as productivity, such as peace, SDG 16, and such as partnership, SDG 17. And that enables us, just like it is today, that the aspect of partnering becomes quite key. So you would notice that in my framing, I put forward planet right at the outset, as it connects to the beauty of the name change, as it brings both civil and environmental. It also brings in the aspect of some kind of dichotomy at times, especially in the times we are in today, that the dichotomy between environment and economic growth. And this is something that we grapple with all the time as we enable our students, which I often think as our prospective engineers, because that's what they are. It's just a matter of time. We think about our researchers, we think about principal investigators, often abbreviated as PI. So in this dichotomy, when it comes to economics and environment, I like to think about the PI with a slight tilt, and I wonder whether it could stand also for a pragmatic innovator, as that aspect of innovation often finds that bridge between this dichotomy, and that is something that we have been known for in, over almost close to 140 years in 2027. And so it bodes quite well for the way that our strategy is. But I talked about those streams, about the other flows that also affect us, which is our relationship with the International Engineering Alliance. The International Engineering Alliance in June 2021 defined a new graduate attribute, and this graduate attribute is engineer and the world. And you may question, why did this actually arrive? But if you think about it in the context of industrial revolutions over time, industrial revolutions have always been there, and they will continue, the fourth and the fifth and so on. But what makes these new industrial revolutions so different to ever before, is that it is in the context of a world that is deeply and heavily connected. What happens if there is a geopolitical shift in another part of the world, it affects us. If there is a change in social dynamic because of the social implications of a technology, it affects us. So whereas in the past you could have graduate attributes that have only a technical inclination, today we find the augmentation of that inclination in the context of the engineer in the world, and therefore that particular shift in the graduate attribute formulation in June 21. So that then mapped with Engineering New Zealand, as it is a signatory of the Washington Accord, which is part of the International Engineering Alliance. And we are finding that shift in our own curriculum and pedagogical innovations. And you will again appreciate that the context of the environmental aspect of engineering comes about there too. But in another stream that relates now closer to the department, as it also had a strategic planning process in August last year, and it had multiple inputs. And I suppose one of those streams would be university faculty, what happens in the region, what happens nationally. And in that mix, one finds that international positioning becomes quite key. And the department looked at, we could look at various ranking instruments, not that they're the only input, they would be one of the inputs. And they looked at not where our position is and then see which are the 10 better ones than us. That's not what they did. They looked at the best 20 in the world. And from there, it became quite a natural formulation that the civil and environmental engineering is a direction that could help our constant thinking and also worked well for the identity and people in the department, but also the wider context of the faculty. So you could immediately see that in this formulation that it is not only the nature of engineering that matters, but also the nurture that engineering brings about from a societal perspective. And that's sort of the basket that comes forward. But I did promise that there would be a commercial break at some point. And I have been accused, I did a presentation to ENGR 101 students and I promised them a commercial break. And then I forgot about it. And then I met one of the students in Countdown and he asked me about this. And we looked at each other with strange, because I couldn't remember my promise. And I wasn't too sure in a class of 900 students, you're never so sure. So I don't want us to have such a experience while you're counting down in future. So the two commercial elements is that if you are a parent or you have in your company a student who may be interested in programs. Now, if the Vice Chancellor was not here, I would have said in the Faculty of Engineering, but since she is here, I will talk about the broader set of programs that we offer in the university that finds information sessions this evening from 6:30 for parents. And for, of course, prospective students, prospective professionals. Today we start a little later since it's Thursday. It's at 6:30 to accommodate for traffic and people that need to go home and do all sort of things. Tomorrow evening, we also cater for Friday events. And tomorrow evening, we have a different event, which is a 3-minute thesis event, which starts at 5:30. I'm not too sure. I've heard rumors that some organizations finished a bit earlier on Fridays, and therefore we have started a bit early. Again, these are rumors. I don't, certainly in the university, I'm not so sure. It is just a Friday. And of course, my last commercial is in the arena of our sponsor today, Contact Energy. And somebody asked me about, that sounds like a very electrical thing. And I said, well, actually, energy is part of our cross-discipline. And whether you think about where AI is infinity, well, it might actually be in that energy limit. But I have been told that between Tim and Nigel, it's not just civil, but it's also civil and mechanical experiences. And amongst the speakers today, you will hear how our disciplines are finding home at times in each other. But my last commercial is please be in contact. With those words, Rajesh, over to you. Thank you.
Thank you, Saurav. It's always difficult to follow you, but I'll try my best. Anyway, look, once again, officially now we have got a new name, Department of Civil and Environmental Engineering. In Terio, it is Te Tari Puhanga Metarahi Metetayo, right? So we have got, why the slide doesn't change? I have to use this. Yeah, okay, that's good. Thank you very much. Yeah. So I would like to once again begin by acknowledging the people who are present here, apart from the dignitaries that I mentioned earlier. Like we have got presence from staff from the department and outside the department across the university. We have got our alumni, our ex-staff, engineers from the profession, and other interested people, and our postgraduate students as well. Right? So thank you for being here. It is a special occasion, and I'm glad to share this special occasion with all of you. This is more than a name change for us. It reflects who we are and what we stand for. And where we want to head in future, going forward from here. Civil and environmental engineering, it's not just about infrastructure, as many would probably misunderstand. It's about people, it's about communities, and a sustainable future. We are proud of our heritage and excited for what's to come there in future. So this is, I think, a good opportunity for us, like for many of us, to reflect back on our history, right? So for many of us, even our staff might not be fully aware of all the background. And for visitors, for our alumni, that is just an opportunity to know a little bit more about how our evolution has been, right? So in 1873, the Canterbury College was founded, which is what we call now University of Canterbury. This was a constituent college of University of New Zealand. And that's the time, actually, the school was found. And in 1888, UC's Faculty of Engineering was formed in a way, right? So maybe not in the structure that we have now, but that was the first in New Zealand at the time. And we, in 1951, we started offering formally a degree in civil engineering, bachelor degree in civil engineering. And 2004 to 2007, that was the period when we adopted or added a new offering to our undergraduate degrees, natural resources engineering, and our name changed to Department of Civil and Natural Resources Engineering. And today, in 2025, we are changing our name to Department of Civil and Environmental Engineering. I will explain the rationale behind that in a few moments. So that's the background. Why civil and environmental engineering? The name, obviously, because we stopped offering natural resources engineering degree after going through a lot of scrutiny and looking at actually how different it is from what we are offering, and is there an alternative way moving forward. So we collectively decided that actually it was the best good decision to stop offering natural resources degree, and that's why the name had to change, right? So the civil and natural resources engineering stopped representing what we do. But why civil and environmental, right? So in terms of rationale, we chose it not casually after consultation and quite extensive consultation with our staff, students, industry, our industry board, alumni, Treaty of Partnership Office, and we also did international benchmarking. And we felt that this is an inclusive name. It captures the multitude of disciplines that we offer in the department, and also provides a distinctly identifiable home to our hundreds of natural resources engineering graduates. It is easily identified and an internationally recognizable name used by most top-ranked university. Actually, in the background document that we put forward for this change, we have done all the studies and found out actually majority of top universities identify by using civil and environmental engineering. It is forward-looking because it facilitates more inclusive community engagement and stronger and durable partnerships with our external stakeholders, which fosters interdisciplinary research that will lead to smart solutions to address all sorts of societal challenges. Right? And it aligns very well with the Faculty of Engineering and University of Canterbury's strategic goals, and also aligns well with the new graduate attribute, the engineer and the world, required for accreditation to Washington Accord for our degrees. Right? Now, many of you know, but what we do, although the name is Civil and Environmental Engineering, actually the department's offerings actually can be divided into two broad categories. One is built infrastructure, the second is natural environment. And there are several identifiable disciplines and themes within those two subcategories. But you can see that many of what we do actually span across the two, built environment and built infrastructure and natural environment, like the earthquake engineering, fire, geotech system, right? And there are other disciplines which align closely with one of the two. And to cover that, like to be as broad as possible, we have to offer a number of programs, unlike several other departments which might have only one or two offerings. We have a multitude of offerings there. You can see our Bachelor of Engineering in Civil Engineering has two minor. One is Structural Engineering, the second is Water and Environmental Systems. So probably the name Civil and Environmental actually covers the two areas there. The degree in Natural Resources Engineering, which you used to offer, is no longer offered, hence the need to change the name. We have got several taught master's degrees specializing in different themes or different disciplines. And in addition to that, we have got research-based qualification, top-level postgraduate qualification, including PhD and Master of Engineering. And not only teaching, actually, even in research, we have got resources. When resources, we talk about resources, the most important resources is the brain that we have, like people that we have. That's the most important, no doubt. But still, like even the brain comes with ideas, we need tools and facilities to implement the ideas and come with the products, right? So that's where the facilities become important. And we do have world-class facilities to facilitate the research that we want to do, our staff want to do, our students want to do. And some of these are shown there. And you can get further information from our website if you are interested to know a little bit more about those. And in terms of who we are, in terms of our students, we have got 2,500 plus students in terms of head count, but many of them are doing part-time or only a partial, partial enrollment in different courses. So in terms of equivalent full-time, we have got 942, and our female population is 27.6%. It has increased. Don't have the data to show, but I know from memory that it has increased over the last few years. So encouraging sign there, and the breakdown for different ethnicity and postgraduate and undergraduate, domestic and international are shown there. In terms of staff, yeah, it is being led by myself with Brendan Bradley and Rebecca Peer as associate heads looking after the research portfolio and academic portfolio. The total staff in the department around 100, where the academic is close to 50. There are research staff, postdocs and research associates around 15. Technical support, because we have got several facilities which are key to our teaching and research. So we need technical staff around 25, and support staff, other support staff, IT and support staff are 10. We do communicate regularly with a group of industry leaders who collectively we identify as our industry advisory board. And currently the chair of our industry advisory board is Amber Murphy. She works in Baker. And just Helen Trappett, she finished her term as the chair for the last 3 years. She was the chair. And this is currently the composition of our board. So regularly we meet with them, discuss with them any sort of, plan in terms of curriculum change, need to change, how industry is finding our graduates, whether there are any things that we need to be aware of and make a kind of like forward-looking move to meet the future need of the profession. So we do that through the industry advisory board. And when we look at our academic staff, we have got a diverse range of academic staff, like who come from all over the world. It is purely an international team. And not only the origin is international, but they come from top universities in the world, like you name it, Stanford, Berkeley, like Cambridge, Tokyo, and others. And not only that, their expertise is at top level and distributed across a wide spectrum as is required by the nature of the discipline, nature of the department, multidisciplinary department we are. And in terms of the department, we have, put forward through our civil and environmental engineering mission statement. So the mission statement that we use is engineering for civilization in a more sustainable world through, internationally acclaimed research and innovation, future-focused, inclusive, and global leading engineering education, including indigenous values and wisdom into engineering education, research, and innovation, and connecting our educational and research excellence into positive, lasting outcomes that benefit the profession, industry, and wider society. And these all align very closely with what the university values and strategy is, and also Faculty of Engineering. So Tika, Pono, and Aroha, like doing what is right with integrity and empathy, and based on the 3 principles of Tiakitanga, Whanaungatanga, and Manaakitanga, right? So we developed those keeping in mind that actually we want to align with what the university and the faculty want us to be. Oh, sorry for that. Oh no. See values. So in terms of to align with that, actually we developed our value statements. So value the unique and different contributions that make us stronger team by different measures. Trust, respect, and empower, support, and inspire others to create and sustain strong relationships and collaborations, right? Taking care of our people and our stakeholders, partners. Work collegially and authentically, collaborate to achieve our shared purpose, and respect the Treaty of Waitangi and its principles, right? So these to align with those. Now going to my last slide. So looking ahead, where do we want to be, right? So the challenges that we face today, whether it's climate change or disaster resilience, they are too complex for any one discipline alone. We are committed to working across fields, collaborating with experts in different associated affiliated fields like architecture, data science, environmental policy, and more. Our work is not just about concrete and steel. It's about building systems and communities that can stand the test of time, adapt to change, and protect the well-being of future generations by preserving our environment. We are not just training engineers, we are nurturing thoughtful, socially conscious leaders who can design with heart and lead with responsibility. Our strength lies in our connections with Mana Whenua, with our industry partners, and with academic collaborators around the world. We are very well connected with them. These relationships enrich our teaching, our research, and our impact. Environmental sustainability is at the core of our work, whether it's through renewable energy, low carbon materials, or climate adaptive design. We are committed to leading the way. Our research has real and lasting impact, and it continues to expand in depth and breadth. We are proud of the legacy we are building for our students, for our community, and for the generations to come. And at the end, I would like to sincerely acknowledge the contribution and the partnership with Engineering New Zealand and Contact Energy. So thank you very much for all that. Thanks a lot. Yeah. So just moving ahead now, we would like to start the technical seminars. We have got two seminars, one from our colleague David Dempsey, and then followed by our industry guests, two guests talking on one topic, right? So first of all, David Dempsey is an associate professor in the department and an expert in, the low carbon and renewable energy and geothermal, all these activities that can help reduce the carbon footprint from the engineering sector. So he has got immense knowledge. So he will be sharing with us actually the work that he's been doing on reducing the carbon dioxide from the engineering, civil engineering related sector. David, up to you.
Crash me, I'm just going to hit buttons here until I get to the right screen. Look at that, very good at hitting buttons. Kia ora koutou. Ko David Dempsey, toko ingoa. I was trying to think this morning of some appropriate high gravity comments to make to kick it off. And I guess what I came up with is that this research I'm about to tell you about, I couldn't really imagine doing it anywhere other than a civil and environmental engineering department. So in that sense, I'm very glad that they gave me a home here about 5 years ago when I moved down from Auckland. And by extension, the Faculty of Engineering and the university itself very kindly welcomed me here. And it's been a great pleasure building things. And the one in particular I want to tell you about is this new research program that we kicked off last year. It's a $10 million MBIE Endeavour program hosted at the department for the next 5 years. And I put this slide up mainly to show you how many friends I have. And, you know, these are the people who are really kind of contributing, I'm looking for the pointer, to the program, helped me put it together. We're going to have a lot of fun over the next little while working on this. Okay. What I'm not talking about is this. I should say, look, the title there says carbon dioxide removal, and I feel the need to define that. This is carbon capture. It's related, but it's not the same as what I'm talking about. Carbon capture probably has a role to play in the future, no doubt. There's already lots of it going on around the world. But it essentially amounts to a fossil fuel industry like we see here, and then you're making some attempt to grab the CO2 as it goes off and then put it back underground. And that goes on, has been for decades, probably will for decades more. We are talking about something different. This is carbon dioxide removal. It's the idea of going into the atmosphere and trying to take molecules of CO2 that have been up there perhaps for decades, emitted in the 50s and the 60s or in the 1880s or whenever it was put up there. There may be a time in the future, there will be a time that comes where we need to be able to pull that directly out of the atmosphere. And that's what our research is all about. I'll offer this as a kind of a motivating slide. So this was a perspective that came out last year in Nature, and you may recognize name-wise David Frame in there in the author list. But this makes the very good point, I think, that in some future that we all want to kind of get to, that's maybe some kind of climate harmony, we are inevitably going to need to be balancing any of our residual emissions with anthropogenic CO2 removal. And I should define why that is and what that is and why that is. I'm going to do it with graphs. There's going to be graphs and there's going to be equations in this seminar. But they're going to be beautiful graphs. I think they had a graphic designer for this one. This is kind of showing you where we are at the moment in terms of, here's industry, this little pink bar, in terms of how much CO2 we're putting up. The land and the oceans are very kindly absorbing a lot of that at the moment. That's the green and the blue bars down here. So there's a bit of a negative. And the balance is this light blue, and it's sort of the steady increase of emissions in our atmosphere. So that's sort of status quo. One of the conversations kind of says, well, maybe if we can reduce the size of industry through decarbonisation, then we can continue to rely on our atmospheres and oceans to soak up CO2, and we get to some kind of balance. And that might be true for very short periods of time, but it's not going to be true for a long time because there are limits in terms of what oceans can just soak up in terms of CO2. So that's not really a long-term prospect. In this country, we seem to be taking a separate path where, yes, we're going to decarbonise. And instead of putting the burden onto oceans, we're going to look to absorb some of that CO2 into the terrestrial biosphere. And we would typically do that by planting some of these pine trees. We do a lot of pine trees in this country. And they're good. I don't have any particular problem with pine trees. They're quite nice to walk around in. And they are pulling CO2 out of the atmosphere at a very competitive price, which is important. But pine trees have drawbacks. One is that they can catch on fire. That means that whatever carbon you're locking up on them is not exactly secure over the long term. From time to time, and perhaps increasingly, we'll have weather events where harvest products might get washed away, and that's a problem as well. So pine trees are a part of the solution, but they're, at least in my view, not the full solution, and that's what we're working on. In fact, this part is what we're working on, trying to grow this little grey bar here. This little grey bar is essentially geological removals, and you will, I hope, agree that it is essentially balancing the pink bar here. This is the future we want to get to, where whatever emissions we cannot avoid in the future, and there's likely to be some, I have no doubt, air travel is, I think, going to be very difficult to solve, or maybe the last one to shift. Whatever ones we're trying to get rid of here, we're going to need to be doing something to remove them ourselves. And how do we do that? So in terms of the relevance for New Zealand, I think we do have some strengths, and I want to try and make a case about why we might do this. For a start, there's the moral argument. And the moral argument basically says, well, a number of years ago, we agreed in this Paris Agreement that we would emit a certain amount of CO2, and that's the green bar, over a period of time. It looks very much like we're on track for the blue bar, which is higher than the green bar, which means we're going over our obligation. We can subtract off that all the pine trees that we've been planting, and that's the white bar. And you can see that leaves a gap, right, of only 100 million tonnes of CO2, which is quite a few million tonnes of CO2 to get rid of. The agreement does make reference to potentially paying overseas countries some kind of penalty that they might soak this up instead. That's going to run somewhere from $5 to $20 billion. And if you can imagine a future where our governments are writing checks to overseas governments to the amount of $5 to $20 billion, sorry, I don't think that's going to happen. So I think we probably need to find homegrown solutions for closing these gaps. Now, if the moral argument is not enough, then there is an economic argument about why you might do this as well. And we have to be realistic about this. No one's going to do this if you're going to go bankrupt immediately. So you have to get paid to do carbon removal. Otherwise, it doesn't work. And McKinsey, which is one of these crystal ball kind of companies, they try and estimate what will happen in the future. And they think carbon dioxide removal globally could be something like $1 trillion market. And if New Zealand has a decent share of that, it's a really good export market because the product that you're exporting is basically just some accounting on a piece of paper that you send off to another company overseas saying, yes, we pulled down a ton of CO2 here, so you can emit a ton of CO2 wherever you are. There's no shipping involved in that. There's postage, I guess. So here's how you do CO2 removal, and there are a lot of different ways of doing it. I'll draw your attention to the right for a start. You can use the ocean. That's currently what we're doing inadvertently. There are a whole bunch of other ways of using the ocean that I won't touch on at all. Not that they aren't good, only that they're not within our project and they're quite tricky. We're doing it here with pine trees at the moment. And then these are the 3 technologies that we are investigating within the research program. But I want to start with what we are doing, which is pine trees, because that's going to be the obvious segue into some of the other technologies that I'll look at. So we have a lot of this in this country. Our pine trees don't look this nice. I was on Google image search, and these look far better than Pinus radiata. But something very interesting has been happening with pine trees recently. One is that you get reimbursed for planting them with these things called NZ units. This makes sense. You're essentially pulling CO2 out of the atmosphere. It's like reverse pollution. So instead of getting a penalty for polluting, you get a reverse penalty. Someone gives you money. And then what happened was that the carbon price went up. That's the orange bar, and it got very high indeed in 2020 and 2022. And if you look at the afforestation rate, which is the blue bar, and that's basically how many forests are getting planted, you'll see that people recognize, all right, well, carbon's getting valuable, let's plant pine trees. And that's how we're in the current situation where now people are asking, maybe it's possible to have too many pine trees. Anyway, so this might be like kind of one pathway for New Zealand. Basically, you keep planting pine trees until there's no space left for them to go. What do you do at that point? Pine trees aren't bad. They are still technology number 1, in my opinion, for sucking CO2 out of the atmosphere. They've had millions of years of evolution to perfect that process and do it at low cost. So the pine tree is still doing something right. We just need to get the carbon out of it and put it somewhere more secure. And the best way, of course, to get carbon out of a pine tree is to set it on fire. So I propose that we do this, but we do it in a very controlled fashion. What we would do is we would take little bits of pine tree and we set them on fire inside of this thing called a boiler. This is a biomass boiler. You can see there's like a little conveyor belt here that's basically rolling up the pieces of pine tree to fall into the top, and then the fuel cycle continues. And then ideally you do something with all of that good energy. Did you know that we get 10% of our energy in the country from bioenergy? Way higher than I would have thought. So bioenergy, we already do a lot of this stuff and it really goes under the radar. But the fact that we already do a lot of it is a real asset. That means we're not starting from scratch, which I think is kind of important. And if you add up all of that biomass that's getting cooked up in there, then we might be emitting something like 1 million tons of CO2 a year through bioenergy, only it's a different kind of CO2. It's a green CO2 that originated in the atmosphere, not a gray CO2 that came from underground. So slightly different and good CO2 to the extent that there is. This one you might recognize as well. This is the Huntly Power Station on the Waikato River. This one burns a lot of this stuff, which is coal, Indonesian coal. I don't know why, every time I read about it, it's always Indonesian coal, like there's scare quotes around that as in they have maybe bad coal or something. I talked to the people who buy the coal there. The reason they get Indonesian coal is because chemically it's very similar to the coal that Huntly was designed for. And if you put the wrong coal into your turbine, then you will break it. So the reason we go to Indonesia is because it has the right chemical characteristics for it. They send it over, it gets burned in the winter so that the lights stay on. What Huntly are looking at doing, very cool, is replacing all of their coal with these suspicious looking pellets, which are actually wood that has been basically treated under high temperature. And you get something that is coal-like that can be dropped in to your coal burning plants. If you did that at Huntly, you'd have about another 500,000 tons a year of green CO2 to work with. And so why I'm talking about this, generating green CO2 is good. And if we let all that green CO2 go back to the atmosphere, you've got something that is roughly net zero, but you probably do need to do some life cycle accounting to get all of those sort of residual emissions that will be contributing, of course. But if you can catch that green CO2 and basically stick it underground in some kind of storage site, then that's when you go into net negative territory. And you can start, effectively, it's a long pathway, there's a bit of a supply chain, but you're basically pulling CO2 out of the atmosphere and you're trying to do it cost effectively. All right, so this brings me to geothermal systems, which is another topic of interest for me for a long time. And the reason I put a geothermal system up here is because they have been injecting carbon dioxide underground for a while now. Particularly up in the far north, they've been doing it for several years. Over in Iceland, they've been doing it for 10 years or more. And so a geothermal system naturally has a whole bunch of CO2 in it. It's circulating it around the deep crust, going down to some 8 kilometers. Some of it kind of bubbles up and then hangs around in these reservoirs. We stick wells into the reservoirs. We generate electricity with the hot water, and there'll be more on that a bit later. But later on, and more recently, some of the companies are working out how to capture the CO2 emissions and stick them back underground so that our geothermal assets now are also close to net zero. Originally, they had some residual emissions. And so the idea we've been looking at is, all right, well, if we're already doing this, and we are, maybe we could just stick some extra green CO2 in it as well as a kind of a low-cost way of getting some negative emissions there. So of course, naturally, first thing to do is to put together a first-order linear differential equation to solve this particular problem. And this is one I've been playing around with. And the reason I like this is because I can solve the same one in my math courses with the students. And what we're looking at here is basically all of the processes that are important here, including injection. We capture in this one equation, and you can even solve it analytically and get some nice sort of closed form solutions. And it looks like this. So this will be the only graph you really have to interpret here. But along the axis, I've got time in a log scale. And then upwards from 0 is positive emissions, downwards is negative emissions. The dashed line here is me trying to pump lots more extra CO2 into the system. And you can certainly do that. That green is the plant emissions. So this plant has negative emissions. But what you'd find, unfortunately, is this blue arrow. As you push that green one down, the blue arrow goes positive. So basically, as we push more CO2 into the system, you get more CO2 naturally rising up through the system, which kind of makes sense. These things, they can't have infinite amounts of storage. And this is true except in all situations I've tested, except for one where we have something called mineralization. That's this heavy dash line. So when you have mineralization happening, basically your CO2 is turning into stone within the reservoir, then you can have a situation where you don't have it all pouring out the top and you're getting permanent storage in these kinds of systems. So there's a lot of complexity. You've got to work out where the CO2 is going, try and track it over time, do some accounting, figure out if you can turn it into rock. I think the turning it into rock is going to be like the key part of doing all of this. So it brings me onto the rocks. This is one of the nice rocks they have in Iceland. It's called a basalt. In this industry, everyone loves basalts. Unfortunately, the place where we have the most basalt here is in Auckland, one of the things that they can claim. There are pockets of it around the country as well, but this is the Iceland basalt, and they dug this out of one of their geothermal systems. That white stuff on the rock is called calcite, and that is the mineralized CO2 that they injected. Here is the chemical reaction, but basically you've got these calcium aluminosilicates, and then you've got CO2 and water mixed together, and the reaction is such that you end up with this calcite. And the point here is that the CO2 has been locked up into stone and some other stuff, whatever it happens to be. So part of our research is going to be looking at, all right, well, that's great, it happens in Iceland. Is it going to happen here in New Zealand because we've got different rocks? And if it isn't, what can we do to make it or to shift it along? So I've got some very talented colleagues up in Auckland, and they work on things like this. And you can see here, this is a little core that they tried to do these experiments on. It's a basalt. This is a pore space, so we're looking at very small kinds of areas here. But these little crystals are the calcium carbonates growing out into that empty pore space. You can track this stuff in real time and work out how much, and then sort of extrapolate into the future and say, all right, was that going to be millions of tons, or is it going to be hundreds of grams? You know, that probably makes a difference in terms of whether or not you can sell this as a business. Anyway, as I say, New Zealand doesn't have a lot of basalt, unfortunately, like Iceland does. So mineralization route is going to be tough unless we can find other ways to do it. And if you want to get mineralization to occur, then you need ions, and you need very particular ions. You need Ca, you need calcium, magnesium, or iron. And you can see what's in common with all those irons are all the 2+ ones. Those are the really valuable ones that people are working out. So the question is like, all right, well, where can we get more of those to jam into a geothermal system? And one of the cool things, in my opinion, is that actually this stuff here, this is what comes out the other end of a biomass boiler. It's the ash. That stuff, so the pine trees again, contains heaps of calcium oxide. That stuff there. So it's already got lots of that calcium 2+, and we might already have ready access to a bunch of it just in some of the waste streams of the products that we're dealing with. So there might be a solution here for this mineralization problem that we can get straight into. There is a problem though. So this is the UC boiler where we produce a lot of this biomass ash. And it's not just us that have realized that there's value in this stuff. You've got to compete with a Canadian who wants to put this stuff into concrete, of course. So this is Alan Scott. He's working with us on the project as well, looking at ways in which this stuff can be basically shoved into cement or concrete. He's told me 100 times and I still can't remember the difference. But basically you can use it to replace, and then you get certain characteristics, and maybe you need less of the high emissions stuff that would otherwise go into the cement. So anyway, we're going to have to work out some kind of benefits sharing arrangement with the biomass ash, but I think there are lots of potential applications for it. All right. Probably the last rocks that I will show. This is the Dun Mountain in Nelson. You will recognize that it looks very red. That will be relevant very soon. And not much grows there. The reason it is red is because it is largely comprised of a rock called dunite. It was presumably named for the location. And dunite is interesting, again, because still on the theme of particular ions that we're after, this one has lots of magnesium in it. So it's a magnesium 2+ rich. It's called an ultramafic rock. We have loads of it in New Zealand, which is valuable for all sorts of reasons, including natural hydrogen, including carbon mineralization. And it mainly comes from olivine crystals. But the key thing about dunite is it's not new, and in fact, farmers have been using it for a long time. Companies like Balance have been basically quarrying this stuff, grinding it up, and then they just spread it on pasture as a soil amendment for whichever crops need more magnesium or, in the soil for better growth. So we already have a situation where we grab a lot of this rock and we put it on a pasture. We're just proposing really to do more of that. So that brings me on to the last technology, which is called rock weathering that we're investigating. This is by a team up in Waikato. They've been doing this for a number of years now. But rock weathering is a natural part of New Zealand's carbon cycle. So it goes on all the time for millions of years. And basically those ultramafic rocks I just showed you, which is magnesium rich, they naturally react with the CO2 in rainwater all the time, whether people are here or not. And they produce these bicarbonate ions. And so the CO2 basically gets locked up into a bicarbonate ion. From there, it's dissolved in water, it's aqueous, so it gets flushed out to the ocean, where it can later recombine with those magnesium ions, and basically will end up in lots of different forms, but maybe, friendly little sea creatures or shells or plankton or whatever it ends up in, a permanent locked away carbon. So that's a natural cycle. It buffers how much CO2 is in the atmosphere over millions of years. The last technology we're looking at, that's called rock weathering, is just enhanced rock weathering. It's just what can we do from an engineering perspective to speed this up as much as possible. And it turns out it's very basic. You basically go to one of these mountains and you quarry them as much as you can, and then you grind that mineral up into very small particles, so you get very small, a lot of surface area for that reaction to occur on. You spread it out on pasture where you're naturally going to get a lot of rain coming down, taking CO2 with it. And, many of our farming locations are well draining, so you naturally have routes to flush those bicarbonates out to the ocean. And that's it in cycle. It's shockingly simple and low tech. Where the problems arise are that it's really difficult to measure if it actually works. It's very hard to measure how much CO2 has been removed. And if you can't do that, you can't get someone to pay you for it. And if you can't sell this, then no one's going to want to do it. The other thing is that when you start talking to the average person about quarrying rock into a fine powder, spreading it out on their farms, allowing it to flush into waterways, some people start wondering if there are any other sort of steps that you're going to talk about, particularly regards to environmental impact. And so the research has to look at all of these things as well, balances of what's going into waterways and what the effects are going to be on there. But anyway, it's promising because it's very scalable. Lastly, I'll mention some of my good colleagues in the systems group, so that's Beck and Yannick, have agreed to very kindly do a treatment of CO2, much how they have been doing for hydrogen recently. And so this is imagining kind of like a future where if we're doing a lot of this around the country, then we're likely to have some kind of distribution where some people are going to be running their bioenergy factories, maybe at Huntly. We might be sticking CO2 in some places underground, possibly in Taranaki. We might be diverting some of that CO2 for food and beverage or horticulture or e-fuels, and we're going to need to basically move it around in pipelines. And so there's a big kind of like step back and look at the whole system piece where you sort of say, well, where would you start? What kind of pilot studies would you put in? What sort of policies would make this work? How much is it going to cost overall? And that's the sort of work that they're doing, which I'm very excited about. Lastly, I've focused mainly here on the technical work, but I think when we started this, we recognized that there are a lot of non-technical challenges for doing any kind of carbon removal like this in New Zealand. And so we've actually built quite a large team of, I'll say in particular, we've got some legal academics who are going to look at things like, that's fine, you can do this, but is it even going to qualify for a reward under the ETS? Which is no, not at the moment. Could you sell it overseas? What are the international trading agreements going to look like? People looking at the environmental regulations about whether or not there are hurdles there. And then we're working with a number of iwi partners up in the Taupo region, looking at how elements of this could be integrated into, for example, some of their regenerative farming businesses, or others have these kind of geothermal bioenergy precincts. Would aspects of this work in there? The general public. I describe this to people and I get either glazed eyes or a little bit of hostility. I've worked out the general public don't want global warming, but they also don't want high costs of living, which is challenging. And when you describe some of these potential solutions, there's an element of persuasion that goes on, I think. So one of the things we have, many of you may have met Olivia already, has come on board, not just to help me run this project, but also to help come up with a communication strategy that we can talk to people about the challenges and whether or not this stuff is worth doing and what some of the trade-offs are likely to be. Lastly, although I would love to have the money to spend on this to make it a reality, I'm still paying off a mortgage. There's no way that scientists are going to be able to actually implement this stuff, I don't think. And so really, if we're going to do this at large scale, and it has to be at large scale, startups are great, but they take a long time to scale as well. You need to go to industry, and that's why we've been spending a lot of effort finding stakeholders, agriculture, forestry, energy, people who might down the track be able to implement some of this stuff at scale, either because they've got some parts already. I told you that 10% of bioenergy. There's a bunch of geothermal storage, oil and gas, potentially storage. Parts of this are already there. We just kind of need to connect those people together. And then there's an element of time pressure in the sense that it would be great it would be great to work on these things for 2 decades and sort of like work out all the details before deploying. It does not feel like a kind of a 2-decade problem. These technologies are often called backstop technologies, which is really ominous when you get to the definition of a backstop technology. A backstop technology is something you hope you don't ever have to use unless things get really, really bad. So anyway, in one sense, we're developing this because we can't see any other alternative to it in the future. So anyway, I'm very happy to talk about these topics, of course, with any of you. And if you have ideas on how we could be doing it better, then it would be great to have those discussions. But that's me done. So thank you very much for your attention.
Because of the time pressure, probably we will leave the question answer to the end. If we have time, we will have a combined question answer few minutes, but I would like to invite Pritha to introduce our next speakers.
Tēnā koutou katoa, e whānau mai e Otipoti ko Kapoko te maunga, ko Waipota te kaupanga, ko McCrimmon Robinson toko whānau, ko Fritha toko ingoa, ke ototahi e nānei. Thank you very much for inviting me here today. I'm proud to be back at University of Canterbury, where I graduated at the Department of Civil and Natural Resources Engineering in 2011. It's always a pleasure to return and connect with the people and the place that shaped my journey. Today, I'm wearing my Engineering New Zealand hat as branch chair for Canterbury. I want to, on behalf of Engineering New Zealand, celebrate an exciting milestone, the department's new name, Civil and Environment Engineering. Congratulations to everyone involved in making this inclusive, thoughtful and forward-focused change. It's a name that better reflects the evolving challenges and opportunities in our field. I've been collaborating with UC on how we can strengthen the connection between UC and Engineering New Zealand. We want Engineering New Zealand to be a platform that helps showcase the incredible work that's happening here at UC to the broader industry. With my connections with both UC and Engineering New Zealand, I hope to help bridge that gap and foster stronger ties. I hope, for example, we can share some of the presentation that you've done today. Very interesting. I now pass on to the next fascinating speakers from Contact Energy, Nigel Barnes and Tim Boyce. Nigel Barnes is a civil engineer graduating from UC 2007. Nigel has 25 years' experience on large international infrastructure roading projects, specialising in project execution. He is passionate about working with contractors and designers to execute memorable projects. Tim Boyce graduated with a mechanical engineering degree and Masters of Engineering Management from University of Canterbury in 2008. Tim has 20 years in the energy sector across project development, construction, operations, strategy, M&A, and trading. Between 2017 and 2021, Tim was project director responsible for developing Contact Energy's geothermal projects on Tauhara field up until final investment decisions. This included $924 million 174 megawatt Tauhara geothermal power station and the 51 megawatt $300 million Te Huka Unit 3 plant. Tim now works as head of wholesale markets at Contact and is responsible for all of Contact's trading activities. Welcome, Nigel and Tim.
Thank you all. It's fantastic to be back. We've been enjoying our day walking around university today and reminiscing at previous times. Nigel and I were actually at university together, so yeah, met back then and wanted to talk to you today, share a bit about, I guess, what we see as multidisciplinary projects and our experience on the Tauhara project in particular. I think relevant to what the civil engineering department is doing today with the rebrand and the combination with environmental aspects. And I guess real multidisciplinary engineering. we probably don't need to do that. Nigel's going to talk a little bit more about his career, but yeah, my background's in geothermal project development and power station development. I currently head up the wholesale markets and trading function within Contact at the moment.
And you can probably tell by the photo who spends most of their time in an office and perhaps somebody who spends a little bit more time out on site. Yeah, thanks for the introductions. We'll carry on.
Just a quick geothermal 101 before we get into it. Probably, maybe if many of you are familiar with it, perhaps if not, geothermal works by harnessing, at the moment, I guess, you know, sort of 250 to 300 degrees Celsius hot water systems in New Zealand and in our volcanic zone product, primarily around the Taupo area. We're drilling production wells, which are shown on the left-hand side there, into the ground, typically a distance of 1,200 to 1,500 meters, taking the geothermal water, steam and hot water up to the surface, running them through a thing called a separation plant, and we'll talk to you a little bit about that over the course of the presentation. Typically then using the steam from the separation plant to drive a steam turbine, just like you would in a coal-fired facility. We've got a cooling tower which cools that steam down, and then the waste and unwanted water is re-injected back through a re-injection well. So that's what David was talking about before. Adding the carbon back into that re-injection system can send that carbon back underground. So that's a quick 101 on geothermal systems. So some of the nomenclature and names we'll use as we go along. And we're also going to cheat at this point in time. We've got a 30-minute presentation and we're going to show a 9-minute video. So it is pretty interesting. It's got a bit of music. We'll turn that down. If you want to ask questions along the way, please do. But shows the journey of the Tauhara project pretty much from woe to go. So shows a bit on the scale of the geothermal power station that's been built. Just turn that down a little bit because it's quite loud. All right, that's us. Oh, it's going to go again. Excuse me. Here we go. So look, just a little bit about the Tauhara Power Station before we stand here. You know, it's a large-scale geothermal plant. So just shy of $1 billion all told budget, but really proud of, I guess, its environmental and market attributes. So, you know, it's the equivalent of when we've displaced around portfolio combined cycle gas turbines, about 500,000 tonnes of carbon dioxide removal and direct emissions in the year. And it's about 3.5% of New Zealand's power, been ticking away since May 2024, very reliably, and is, you know, kind of the world's largest single geothermal plant. So really just giving you an idea of the scale of this project. I guess what I wanted to talk to you today before I hand over to Nigel, who's going to give you more of the civil engineering bent, was just multidisciplinary engineering, optimization of renewable energy systems, you know, environmental engineering as I see it at its finest, and how you get to scoping, designing and framing a project like this. When I stepped into the project in 2017, 2018, Contact had actually secured the resource consents for its Tauhara plant about a decade before. Big lull in electricity demand expansion in New Zealand, and we'd sat on these for that period of time. We had a huge consented geothermal take. This field is probably world scale. It's probably the largest undeveloped geothermal plant in the world. And so we knew we had you know, a really fantastic project when the time came. But really, there was a greenfield asset sitting there, and this was the paddock. It's probably a little bit after we started building, but that's what became the power station later. I guess the unknowns for us, though, and that required the optimization, we had a design in mind when we consented the plant in 2012. Was that the right for the market at the moment? Was the contractor base going to be able to achieve that? How would we best configure the project for the life cycle design? You know, we're owners and operators of geothermal power stations. We operate them for 60 plus years. So this is all about, for us, what the lowest possible life cycle cost is for the asset for the future. So we really needed to test that. I guess I just sort of highlight some of the things in a geothermal setting, which I think apply to a number of renewable energy projects that you've got to test along the way. The first one that we looked at was frankly scale. You know, are we better to build a smaller scale plant to start with, or are we better to go to a larger scale setting and I guess get the economies of scale? For us, a smaller scale compact development, look, it's lower cost, lower risk in terms of a reservoir from a geothermal setting. You don't know your reservoir until you've really got it and operate it for a period of time, and probably simpler execution. Larger scale development, like the picture on the right here, does have significant economies of scale benefit, particularly in the capex. But probably more importantly for us as an operator of these plants, you see material long-term O&M savings if you get the scale right. So operation and maintenance is really an important factor for us at Contact. And then the second one is probably more of a commercial stance. And I think, you know, if we're talking about what engineering really is, it's the intersection of, you know, markets, commercials and practical projects. And for us as a company, you know, building a large plant, establishing our foothold into a renewable growth period and getting an associated uplift in earnings as a company level actually enables us to invest in more renewable projects more quickly. So, you know, a really important aspect for us taking on debt and continuing with our development pipeline. The second kind of optimization for us on a geothermal plant like Tauhara was really technology driven. Geothermal plant producers are not dime a dozen. You can't ring up, you know, your Hawkins, your Fulton Hogans, these people of the world and say, I'm building a bridge here. There are 5 credible parties who build them internationally. 3 of them have experience in New Zealand. They offer plants across 2 different technology types. So on the left there, we have a binary plant. It's an organic Rankine cycle for those who like their mechanical cycles. And on the right, we have a steam turbine configuration. For us, you know, critical is to understand which of those is going to be, again, the best life cycle opportunity to have on the plant in future. What's the trade-off between CapEx, plant efficiency and performance, long-term O&M costs, viability with the reservoir and how the reservoir trends might change over time. So we looked at this as well back in 2018 and 2019. And then the third piece I wanted to touch upon is just how interwoven a system like this is. So once we've chosen a plant, they actually have a different design configuration upstream of them. So a geothermal plant, as I said, relies on hot water and steam coming out of the ground and going to a separation facility, a separation plant. If we're building a binary plant, which was the left-hand side of the last screen, we've got a single phase to separate the fluid with. If we're building a large-scale steam turbine plant, we can have up to 3 geothermal flash systems. So that's what's on the right-hand side there. And I guess, you know, you're beholden to that. So you choose your plant technology and you've basically got to deliver the separation plant as an owner of these plants and a builder. But there's a significant difference in complexity between the left-hand side, that single separation, and the triple pressure separation plant. I touch upon this because Nigel will then go into what challenges you have when you're trying to do a design with, you know, that level of complexity on the triple flash system. For us, I guess key pre-COVID 2019, 2020 was testing the market in this. So we did a very extensive tender process. We invited 4 of those international parties to come. One sort of, you know, probably wasn't capable in New Zealand setting, but the other 3 all submitted bids for this plant. And we ultimately decided that we wanted to go for a large scale plant. Just the uplift in earnings and the lifecycle cost of going to a larger development really outweighed, just delivered material benefits for Contact. And so we took 4 binary units and a single flash and a triple flash steam turbine into a competitive power station tender process. Might not mean a whole bunch to you, but from a civil design perspective, and this is what Nigel will get into, you know, material differences in what you're having to design for between those 2 plants. A binary plant, far bigger earthworks, far bigger footprint, but quite simple foundation design. Not many material foundations around the plant, but you do have some other aspects. The plant is a hazardous material. There's explosion risks, underground and environmental considerations and handling that isopentane material are really important. And so, you know, sort of set the tone for what would have been required from a design perspective if you're building the binary plants. Flip side, if you've got a large steam turbine, and that's what we ended up building, so you saw the visual of it there, significant elevated platform akin to a large bridge with significant forces on it. The superstructure on that 8 column design with, I think there's about 130 something piles ultimately in the turbine hall, makes for a major civil and structural design brief for that project. You've also got the large cooling tower basin. It's 200 meter high tensile pre-tension slab, and the triple flash separation plant, which we talked about before. So quite a different civil design brief between the 2 projects. And this, you know, at final investment decision, and where probably I stepped out of the project and Nigel stepped in terms of this presentation, as a visual of what hopefully looks a little bit like what you've seen on the video there. But in the foreground, we've got the separation plant, you know, quite complex, 4 vessels, triple flash system. We've got the geothermal fluid holding pond. Along the back there is the large cooling tower. And in the back, you've got the turbine hall within which the steam turbine is housed. And so that, you know, really drives, you know, the civil design requirements of the project. Really, to get to that point, though, it's been a significant optimization of what the reservoir is doing, the mechanical and process design, and, you know, building the brief up for the configuration to come.
Thank you. We are getting on in time, so I'll whiz through it, which is great. Thank you very much, Tim. I'm not the best public speaker, but I'll do my best. Where I'm from and where I've come from, I'm not the biggest academic in the world here, but I have spent many years out in the industry. I'm a bit of a boots on the ground type of engineer. I started off driving excavators in Te Puke, New Zealand. So I ended up coming down here for my best 5 years of my life, and I'm passionate about infrastructure projects and the execution of them. And Contact Energy has, I'm now 5 years in with Contact Energy and onto a 3rd brand new geothermal power station build. Tauhara was my first experience with a big geothermal power station. Civil engineering in energy projects is immense. I cannot tell you that in any greater words. Like what you've just seen on the video, it still stands hairs up on the back of my neck. The amount of concrete and steel that goes into that project was staggering. I'm not going to give you the numbers. I'm going to talk about one particular case around concrete supply that was a challenge in Taupo, but it is one of the biggest infrastructure projects in New Zealand, and I've had a bit of experience overseas that Contact should be proud of, and that we are as collectively very proud of. For me, civil engineering is sorry, I might just go back a step, because I just want to, civil engineering for me is not just about working in a design house. It's actually about having some boots on the ground, having some exposure with our designers and actually executing projects. That's what it is for me. So civil execution, yeah, combination of those things there, enabling works, earthworks, in-ground civils, buildings, foundations, ponds, and other storage devices. And I'm sort of speaking specifically around geothermal plants there, but Tauhara had it all, and it had it all on steroids. Hello, Warren Poe, how are you? Key for success civil execution in these geothermal power station projects, definition, like we need to define that project well. Lots of learnings from Tauhara. We're now into our third power station build and we've got the definition nailed down. We know our battery limits of where we can design to and where we can build to in parallel. Civil engineering, they want it built first, but it's very much driven by the mechanical process design that's happening at the back end. But we need to find that happy medium and maturity to allow for us to progress with that civil engineering and the civil engineering execution. One of our issues in Taupo was concrete supply. Tens of thousands of cubes of concrete poured on this project. Taupo is a small place. There is a ceiling of what is a reasonable supply of concrete for the area. We absolutely devastated the residential concrete market, and for a good period there, for about a couple of years. We understood, and working with our suppliers, that a max pour size was around 600 cube in Taupo. In Auckland, you could probably do that any day of the week. Any other major city, you can do that and more. Taupo, you've got 2 batching plants with limited trucks, limited aggregates, limited sand, limited cementitious, supplementary cementitious materials. I'll get onto that. So we've got to turn that into that, but we want that early. So we need to build in enough flexibility to allow for all of that future structure to be on there. That's what I talk about, design maturity. There's a lot of words here, but I want to talk about these words because I've mentioned 600Q. Contact Energy's requirements have some reasonably high durability requirements around supplementary cementitious materials, fly ash in our mixes because of the geothermal fluids in the ground. We had to go and help out our local Firth batching plant to build a new foundation and silos so they could have more fly ash on site. We also built new storage areas for aggregates and sand so that they can actually get more on site in their batching plants to supply us. They had trucks from out of town. We had to combine Firth and allied mixing plants together so that we could get some pours done. They adopted the same cements, believe it or not. The size is just immense. I can't stop talking about how big and how diverse some of these pours were. My next one was, and if anyone out here wants to do a bit of a study on bentonite reacting with hot dip galvanized reinforcement, feel free. Very open to a discussion with you about that. Early days, because of our Contact Energy's requirements around geothermal fluids and durability of our mix designs, of our plant, we called up galvanized reinforcement in some of our structures, critical structures. So that meant our piles underneath our turbine pedestal. It was below water table. Our piles were minus 25 meters below finished ground levels. They were in below the water table. So we needed obviously bentonite as drilling fluids to support the shaft, but our owner's requirements, being Contact's owner's requirements, needed galvanized reinforcement to be used. But bentonite reacts with galvanized reinforcement. And that was a bit of a challenge for us because it was probably reasonably late in the piece that we found out about that. So we had to design that out in regards to, we forgo the requirement for the galvanized reinforcement, but we did a bit more design in and around concrete design and crack control within a pile. Health and safety, I want to touch on this because it's important to me. Over 2.5 million man hours out there on that site without an incident to speak of. Maximum 651 people out there in any one day on that site. Huge numbers to have through the door on any one day to execute that project and execute it safely. My role as a civil engineer isn't just civil engineering and project execution. It's actually me on eyes and ears on the ground. I'm talking with our construction managers, construction supervisors. So I guess that's always an aspect for me and for us as we go out and become better civil and environmental engineers. Tim?
Yeah, we sort of put something together a little bit, but, you know, like anything, speaking to an audience like this, you know, civil engineering professions, young professional engineers, you've got to be honest with yourselves too, right? And learn some lessons. So probably put a few up here, which I think Nigel and I compared notes on, and I think will probably resonate with many of you. For me, you know, big success in the project. It's up and running. It's been fantastic. You know, there's a much publicised energy crisis late last year. This plant ran through that uninterrupted, right? So if it hadn't been for that last winter, I don't quite know what the situation would have been, but it would have been higher prices for much longer, much earlier, right? So immensely proud of that. We've got its life cycle design at its core. I'm very convinced of that now. So that configuration, that plant can adjust to the reservoir. We'll make changes. We can reconfigure things as the time progresses, and it is already proving to be a very low cost O&M operation, which really for us is a highly important aspect of engineering design. But, you know, being honest with yourself, we got Nigel in at final investment decision on the project, right? We need to bring people like that, multidisciplinary engineering, high levels of communication and collaboration as early as you possibly can on all these projects, right? So I credit the rebranding of the civil engineering school to civil environmental engineering. You're stepping in the right direction of how engineering is, you know, in the commercial and the project world. It is not one entity in isolation working by themselves. It is a whole bunch of people working together. Get those teams in place early. Small and nimble teams, really important, I think. You know, you can actually get a little bit lost in larger teams. Keep your teams, you know, with a really great skill set, tight and cool and can control the project and speaking to each other. The other one is, you know, defining the project. I talked a lot at the start. Biggest lesson for me, you know, we've got a fantastic selected project, and we thought we were ready to go. We needed to do an immense more work on the definition of the mechanical process in civil design. We needed 6 months extra, basically, if I thought about it. We just tacked that on to the end of the project, and it cost us money. So if we had our time again, we would have done 6 more months work at the start. Probably would have finished at the same time, I think, and would have saved ourselves a lot of money. So you've got to work that out and learn these lessons. Granularity and preparation is pretty much everything. I did say there, you know, it's one thing for me personally, you know, if you want to get a really defined project and get a really great budget, you know, that's good. Like I talked about, we should have done that. Or otherwise, give yourself a large amount of contingency for time. Figure it out at the end if you just need to go. And I think that's pretty much us. So again, 20 minutes of presentation and 9 minutes of videos, but yeah. Thank you.
Thank you, Nigel and Tim. And thanks, Preetha, for introducing them. And thanks, David. Unfortunately, because I've been told that the room is booked after 4, so we have to be out of here. So we don't have much time left. So I know that if there will be questions, but we can provide the contacts of our expert speakers, and then you can always contact with them and then ask your queries to them. We can't do that because of time today. The next step is actually we have got a little bit of Kai, but after the Kai, if any of you are interested in a short lab tour of some of the facilities of the department, Dave Carney and in his team, they will be waiting just outside, and you can, after the Kai, probably just contact him, and he will guide you, and his team will guide you through, right? So if you are interested. But before we go there, I would like to invite Liz to just bless the food before we go inside that. Thank you, Liz.
No mai ngā hua o te whenua o te ngahere o te waitai o te wai Māori. Hei oranga o tātou tinana, kia ora.